Hi everyone, I'm Hu Xin from National University of Singapore. The topic of this paper is a miniature manipulator with variable stiffness and towards minimal invasive transluminal endoscopic surgery. The content includes introduction, system description, analysis, experimental verification, and conclusion. As we know, the advantages of minimal invasive surgery causes smaller trauma, less pain, and faster recovery. As a typical kind of MIS, natural orifice transluminal endoscopic surgery can minimize the invasiveness of patients. Currently, widely used medical instruments in MIS are divided into two types, flexible and rigid. A flexible instrument can increase the level of safety and maneuverability, while rigid instruments can deliver high payload and accuracy. Therefore, to combine the advantages, our paper proposed a miniature manipulator with variable stiffness, and we try to integrate compact size, flexibility, and dexterity for surgical robotics in MIS. Firstly, I'll show you the whole system briefly. The left model is the miniature manipulator with variable stiffness, and the right model is the driver system. It is detachable, and this is the prototype of the robotic system. For manipulator, it consists of 4 steps and 4 modules. Each color corresponds to each module. They are driven by wire ropes with flexible tubes. They allow the driver system to be put far away. There are holes in the side wall of 4 step and module. They provide channels for wire ropes. From the picture, we can find the manipulator has 6 degrees of freedom, grasping, bending, wrist rotation, 2 unfoldings, and translation. All joints are driven separately, which can avoid complex motion planning. For driver system, from the picture, we can find it can be divided in 2 layers, the upper layer and the lower layer. This can help surgeons to change the manipulator quickly during an operation. And besides, the rails and the worn gears are used to drive the manipulators via wire ropes with flexible tubes. From this table, we know the actuation relationship in detail. Each driver unit controls corresponding module. For example, the wrist module is a green link. It is driven by wire rope 3 and wire rope 4. These wire ropes are extended to this driver unit. The springs here are used as serial elastic actuation. The bending module, the original one, is driven by wire rope 7 and wire rope 9, and the springs are used for variable stiffness. And for others, so on so forth. After showing the hardware, we perform some analysis. The first analysis is the robotic kinematics. Firstly, according to the robotic coordinate system and the DH table, the forward kinematics of the manipulator can be deduced as follows. And based on forward kinematics, we can solve the analytical expressions of inverse kinematics, shown as the equations of each joint. To validate the workspace, we make workspace characterization in both simulation and physical robot. Firstly, we use MATLAB to simulate the workspace based on the forward kinematics. Results show that the workspace covers a volume of 25 mm in length, 16 in width, and 20 mm in height. This workspace is enough for the natural orifice transluminal surgery. Secondly, we conduct the workspace test in physical robot. Each video shows the movement of each joint, the opening angle of the forceps, and the rotational angle of the wrist joint, and the radial translation of the wrist, and the 2 unfolding joints, and the radial translation achieved by the joint 4 and 5. The maximum movements of each joint are shown here. The opening angle of forceps was 60 degrees. The rotational angle of the wrist joint was 45 degrees. The radial translation of the wrist was 5 mm. The inward bending angle and the outward bending angle were both 30 degree. These two picture. The radial translation achieved by joint 4 and 5 was 5 millimeter. Next analysis is about variable stiffness. Firstly, I show you the mechanism of variable stiffness. The motion of joint is controlled by pulling Y-1 and Y-2. Y-2 is driven by position control, Y-1 is driven by force control by this spring. The stiffness of the joint is determined by pulling force of Y-1. Y-1 is attached to this spring, which means the pulling force of Y-1 is equal to the compressive force of the spring. This force of the spring is positively related with length of variation of the spring, which is determined by length variation of Y-1 and the rotation of worm gear. Therefore, the rotation of the worm gear can control the joint stiffness with length of variation of the spring. For example, if the worm gear rotates clockwise, it can pull the slide push the spring push another slide. This slide can pull the Y-1. So the Y-1 will be pulled, so the stiffness will increase. After analysis, we did some experiments to verify the performance of the robotic system. The first experiment is to measure the grasping force. The experimental setup is shown as this figure. The manipulator was fixed to the support. The terminal of the force meter was attached to the forceps via a wide rope. Okay, so then I show the video of experiment. From the video, we can see the forceps was driven to rotate with the tension readings displayed on the force meter screen from 0 to largest 3.31 Newton. It means that grasping force achieved by the forceps is larger than 3 Newton. This grasping force is enough for natural orifice transluminal surgery. The second experiment is to test the variable stiffness. The experimental setup is shown here. The manipulator was fixed on the spot. A force sensor was mounted to the motion stage. The micro head was rotated to drive the full sensor to move from 0 to 2 millimeter with a step of 0.5 millimeter. Repeating the experiment repeats 5 times. Then I show you the video. For our robots, we change the stiffness on these two joints or these two directions. We measure the forces in two conditions, high stiffness and low stiffness. The red line shows the low stiffness and the blue line is high stiffness. For direction 1, the stiffness of two states is 0.42 Newton per millimeter and 0.3 Newton per millimeter with a change rate of 2.45. In direction 2, the stiffness in two states is 0.42 Newton millimeter and 0.71 Newton millimeter with a change rate of 0.69. The change rates of the stiffness are very obvious. This is a performance of test of grasping something. We teleoperated the manipulator to grasp the seeds. The manipulator was placed in a transparent tube with a diameter 20 millimeter. The green chili with seeds was put in front of the manipulator as operation object. We show you the grasping process in this diagram. The manipulator is in initial state, then reach the target region. The process of picking the seeds, and then the manipulator was retrieved from the target region. Finally, the seeds was dropped. This is a video for the performance of test grasping chili seeds. Open forceps, go to the target region, picking up, and pick it up, retrieve, and finally drop it. Finally, we also conducted an extra vivo test to validate the dexterity of manipulator in porcine stomach with compact space. The experimental setup includes the manipulator, an endoscope, porcine stomach monitor. Inside the stomach, we finished the following movements test: through state, translation, bending, rotation, and gripper closing. This is a video for the ex vivo test. Go inside and translation, bending, rotation, gripper closing. In conclusion, the contributions are summarized as follows. A miniature manipulator is proposed, comprised of the carefully designed Holly modules with holes in the side wall. It is compact with a diameter of 4 mm and dexterous with 6 degrees of freedom. The manipulator is driven by wide ropes with flexible tubes, avoiding the distraction caused by kinematic coupling. The manipulator's stiffness tune is achieved by the spring sliding block-based driver system. For the manipulator, the kinematics, workspace, and stiffness are analyzed. Tests in terms of grasping force and variable stiffness are conducted. Finally, the manipulator's performance toward the basic operation procedures is demonstrated in ex vivo test. Okay, thanks for your listening.